have seen the Bayes classifier in different contexts without talking about it as such. And I want to go over different forms that can show up in the literature and show you why they are equivalent. So the Bayes classifier, as we have derived it today, is of the form HB of x is the argmax over k from 0 to k minus 1 of eta k of x. Now what I'm claiming is that an equivalent formulation is the argmax over k of pi k px given y x given k. And the justification here is that I'm using Bayes' rule. So let me write it explicitly. What's going on here is I'm going to be using rule. Why? Because I'm claiming that if you look at HB of x here, it is the argmax over k, and I'm going to write eta k explicitly as the probability of y given x of k given x. Now the maximization is over k. So if I multiply by a function of x, I don't change the value. So without changing the value of my optimization here, I can multiply by px. But once I multiply by px, you see that this quantity is now the joint distribution, by definition, between x and y. And there's nothing that prevents me from expanding it using the other conditional probability and write it as the argmax over k p x given y times py of y. But py of y is exactly what I called pi k by definition. And hence, that expression that I gave you is indeed completely equal. Now, the next form that you might have seen is in the special case of binary classification. In the special case of binary classification, since we only have to compare two quantities, we might as well, instead of comparing if one is greater than the other, compare the ratio and see how it compares to 1. And there's actually nothing that prevents you from taking the log of the ratio and compare the threshold to something else. So formally, I'm claiming that in that specific case, what you have to do to test is compute the log likelihood ratio, the log of p of x given y, x given 1, divided by p of x given y of x given 0, and compare it using a threshold, which is the log of pi 0 over pi 1. So that's weird sign that I am using here. It means I'm using a threshold to decide whether I output 1 or I output 0. I don't think that's a very standard notation, but I find it very convenient. So let's derive it formally so that you see what I have. So what I know is that in the specific case of my binary classification with Bayes classifier, HP of x, according to my second formulation, boils down to taking the argmax over k in this time 0, 1 of pi k times px given y or x given k. So differently, the test I have to make is the following. I have to check that pi 1 px given y x given 1 is indeed greater than or equal to pi 0 px given y of x given 0 to decide 1. Now, if I use my thresholding operator, I would write it as follows. I would write it as such, and I would put a little label 1 here and a little label 0 here, meaning that if the quantity on the left is larger than the quantity of the right, I decide 1, else I decide 0. And you can see that this quantity here that I'm writing is strictly equivalent by taking the ratio, manipulating terms to the left and to the right, to the following. I can say that it's the same thing as comparing the ratio p of x given 1 to p of x given y, x given 0, to a threshold, which would be pi 0 over pi 1. And of course, taking the log doesn't change anything, because log is an increasing function. So this is that logarithmic pi 0 over pi 1. So this is, again, completely equivalent in the special case in which we have only two labels. This log likelihood ratio approach is not so useful if you have more than two labels, because then you actually need to compare all the px given y, x given k, and normalize them to the same one, px given y, x given 0, for instance, and there's no guarantee that you can have a simple expression. Now, if you are in the very specific case in which all your classes are a priori equally likely, which corresponds to the situation where pi 0 is equal to pi 1 is equal to pi k minus 1 and everything in between, then I'm claiming that there is one further simplification that happens. Instead of maximizing or taking the argmax of eta k of x, which is py given x, you can take the argmax of p of x given y. And I think this is again best seen if you again look at the second expression I gave you for the base classifier, in which I told you that we can write the base classifier in general as the argmax over all possible labels k of the product pi k p x given y of x given k. Now, in the specific case where all your a priori probabilities are the same, this pi k here is a constant. If for every k, pi k is equal to the same quantity. And therefore, you can take it out of your maximization, and maximizing py given x is the same thing as maximizing px given y. The one thing I would emphasize, and I can't emphasize that enough, is that in general, this is not the same thing. It is really only the same thing if you can guarantee that your priors, pi k, are all equally likely. So be careful with that, because I can guarantee you that this is where I would see mistakes in the homework. So there's a difference between maximizing p x given y or py given x, and it's only the same thing if your priors are equally likely. So in the lecture note, we can actually derive explicitly a base classifier when we have fairly simple probabilities and fairly simple examples. And so what I will ask you to derive on your own, or by looking at the lecture notes, is that if you assume that I give you a situation where I have a priori label 0, 1, and given 0, I generate my data according to a normal distribution with variance 1 centered at 0, but given 1, I generate it with the same variance but centered at 1. So in that case, you will be able to identify exactly what is the base risk, but also what is the exact base classifier, and it takes a fairly simple expression. One thing I encourage you to do in all the problems that I will assign you is to doodle to get a sense for what's going on. And in that specific example here, even though I'm not going to do the calculation exactly of the base risk and of the base classifier, I'm going to show you how you can initially start thinking about it so that you can guess the answer, making an educated guess that then you have to justify. So let's do that together. So I'm just going to use an illustration here, which is not quite a proof, but it should guide your proof for if you want to check the results here in the lecture notes on your own. What's happening here is the following. The data is 1D, so we can actually plot the distributions on an axis. So what I'm going to plot here is the distribution of the class given x. Given x equals 0, I told you that the distribution px given y is that Gaussian distribution centered at 0. Given 1, I get another distribution which is centered at 1. Plot is not particularly nice here. These are supposed to be identical distributions. Now, given that the distributions are the same, intuitively what you would expect is that the intersection here of these two curves is exactly happening at 1/2. So 1/2 is the point where p of 1/2 given 0 is equal to p of 1/2 given 1. Given that my priors are equally likely, I know that finding the base classifier amounts to finding the argmax of p of x given y, which are the curves I'm drawing here. And so you see that the region that you will classify as 0 is the region to the left of that vertical line at exactly 1/2, because that's exactly where I know that I'm more likely to have label 0. And similarly here, I'm more likely to have label 1. So I haven't done any calculation. I've just done some doodling using what I know about Gaussian distributions and what I know about their symmetry. And the example that I developed in the lecture notes is doing nothing but formalizing that specific example. All of that is very nice. And we could characterize the base classifier quite generally. I'll leave it to you to convince yourself that even though I restricted myself to binary loss functions, it actually does generalize beyond that. But the problem is it hinges on the fact that we know px and py given x, which we don't know in practice. And what we'll see, starting not today, but in the next lecture, is that one very natural thing to do is to try to learn these probabilities that we are missing and use them as if they were the true distributions when using a Bayes classifier. So that seems a pretty big detour. We're saying that we don't know the distributions, let's learn them. And since we know the optimal classifier, if we had the true distribution, let's use our approximations of the true distribution if they were the true ones. And such classifiers are dime a dozen. There are plenty of them out there, and they're called plug-in classifiers because they're effectively learning the distribution and plugging it in the expression of the optimal Bayes classifier that we derived together. So we'll get back to that later. For now, I just want to mention that you can, of course, extend this notion of Bayes classifier much beyond the case that we've studied here. We focused on the risk for a binary loss functions just because it's convenient. I find it very convenient to associate the risk to a probability because then it simplifies my reasoning when I use law of total probabilities, but you can generalize that to loss functions which are bounded. And this is important because there are also many situations where it's not appropriate to just use a binary loss function. And one such situation that I want to mention, because we talked about it in lecture 1, is the fact that there are situations where making an error between labels is not the same. If you think about classifying cats and dogs, it doesn't really matter. You won't pay a bigger penalty for mistaking a cat for a dog or a dog for a cat. But if you're designing a fire alarm, there's a big difference between having a false alarm and a misdetection. And therefore, there are costs that one would want to introduce that capture that. And one such cost is the one that I'm introducing here that corresponds to, if you want, a cost-sensitive loss function, where what I say is that if my true label is 0, and I don't predict as 0, I pay a cost C0. Whereas if my true label is 1, and I classify it as not 1, then I pay a cost C1. And it's possible to extend the Bayes classifier to that specific case, and that's something that I will have you explore as part of the homework. One of the reasons in practice where such cost functions are used is because you might be given a very unbalanced data set. Let's say you were in a weird world where there would be many more cats than dogs, then effectively what happens is that you're much more likely to predict that anything you receive is a cat just because you know that in the world there are more cats than dogs. But ultimately, what you care about as a user is really making sure that you don't always classify a picture as a cat, right? If it's actually likely that it's a dog, you want a dog. And therefore, it would make sense in a case like that to penalize much more not classifying a dog as a dog, to make up for the fact that your data set that you're given from the beginning could be extremely unbalanced. So this concludes my discussion of Bayes classifier. Again, to wrap up, these are conceptual classifiers that you cannot implement in practice because you would need to require the knowledge of the distributions generating your data and your labels, but they're very useful conceptually to understand why there is a lower bound on the true risk that you can go below, and that lower bound might not be 0. And second, they give insight for designing what are called plug-in classifiers. So what you see here is yet another notebook that I'm using to illustrate the Bayes classifier. I'm going to run it live for you again. What's happening here is that in this very synthetic example, I know exactly the distributions I'm using to generate the data. And therefore, I can use that to actually evaluate my Bayes classifier. I'm going a little fast because that's something that I will want you to do in the homework. And the result that you show here is exactly this one, in which I have the same data set as before. On the left side, it's red and blue here. I generated my data in a very specific way, and you'll be able to explain in the homework why in that specific example, my Bayes classifier is given by that straight line. It is indeed a straight line. It has to do with this very specific form of the distribution that I'm using to generate the data red and the data blue. In general, remember, you're not able to simulate the Bayes classifier because you don't know the true distribution. And you'll have to resort to plug-in classifiers.